Okay, when we deal with cell potentials, you'll notice that oftentimes you'll see the little E with the little degree sign up in the corner. And when it has that little degree sign, it means that we are at standard conditions. And when we're at standard conditions, just like a standard temperature and pressure with gases, or delta G standard, delta H standard, there's different standards. And remember that with gases at STP, so this is just for gases, that the pressure is 1 atmosphere and the temperature is 273 Kelvin. Okay, all other times that you're at standard conditions, whether that's enthalpy, delta S, delta G, or the cell potential, it's not, the only thing that's different is the temperature. Okay, it's still 1 atmosphere for gases, 1 molar for solutions, but the temperature is 298. Only for gases is the standard temperature 273. For everything else, it's 298. Okay, but a lot of times, just like with equilibrium and other situations, you can have conditions when you're not at standard. Okay, and when that happens, it means that typically it means that your concentrations aren't 1 molar. Okay, so when conditions are not standard, different voltages than those predicted by that standard reduction potential table will be generated in the cells. So in order to make a prediction about which one is greater, the standard cell potential or the non-standard, we need to consider, this is going back to equilibrium a little bit here, we need to consider the reaction quotient, which is the letter Q. Okay, and in this case, we're not comparing Q to the equilibrium constant. There is no equilibrium constant in this case, okay? But in Unit 6, we learned that when we were not at equilibrium, then we could use Q to determine which way the reaction was going to proceed to reach equilibrium. Well, in this case, again, because we're not at equilibrium, and we're not using equilibrium here at all, what we're doing is we're going to compare Q to the number 1. Okay, and you'll see why when we look at this equation here at the bottom in just a second. But let's say we've got this equation right here, where zinc is a solid, copper is a solid. So your Q equation would be the concentration of Zn2 plus over the concentration of Cu2 plus. Okay, and so there is our Q equation right here. So in addition to concentrations of solutions, so the square brackets, you can also do Q with partial pressures, just like how we did with Kp and Q. Okay, but again, just like equilibrium, you don't include solids, you don't include liquids. So under standard conditions, this is equal to 1 molar, this is equal to 1 molar, and Q is equal to 1. Okay, if Q is equal to 1, then you're at the standard cell potential. So, if the ratios are the same, let's say that the concentration of zinc 2 plus is 0.5 and the concentration of Cu2 plus is 0.5, then Q is also equal to 1. You're still in a non-standard cell because the concentrations aren't 1, but the cell potential is still going to be the same as it would be, because if those concentrations are the same, it's equal to 1. Now, which cell is going to last longer, though? Think about like a battery. Okay, which cell is going to be able to produce electricity for a longer period of time? One that's at standard conditions, 1 molar over 1 molar, or one that's at 0.5 over 0.5. Clearly, the one that is the greater concentration, because it's got a greater number of moles of the zinc and the copper ions. Okay, under circumstances where the ratio of the concentrations computes as something other than 1, then again we have these non-standard conditions. Okay, and again I already talked about, if it's 0.5, it's still non-standard conditions, but Q is still equal to 1, so the cell potential is still the standard cell potential. Okay, now this equation right here is a gigantic mess, but it is given on the AP test, but notice that I do say qualitatively. I can't imagine a question where they're going to ask you to actually solve a problem dealing with this, okay? But just to go over it, and some of this stuff is going to come up later, R again is the gas constant, but it's the 8.3141. The temperature's in Kelvin. N is the moles that are transferred. Remember when we were talking earlier about how many electrons transfer from one equation to the other, in whichever one's losing electrons to which one's gaining? That's the N value here. And F is something that's called Faraday's constant. We're going to get into both of these a little bit later on. I really don't want you to worry about this component right here at all. All you really need to know is all of those are positive values. So if Q is less than 1, then the natural log of Q when Q is less than 1 equals a negative value. Okay? And if it's a negative value, then you're subtracting a negative value. You're subtracting a negative value. And in that case, the E cell is greater than the E cell standard. Okay? The natural log of Q when Q is greater than 1 is positive. And then you're subtracting a positive value. So E cell is less than the standard cell potential. So this one is the non-standard cell potential. These with the degree sign are the standard cell potentials. So when Q equals 1, again, even if it's 0.5 and 0.5, you are at the standard value. You are at the standard cell potential. When Q is less than 1, and listen to how I say this, again, usually that when Q is less than 1, that means you have a large concentration of reactants compared to the products. Okay, this combination increases the driving force for the forward reaction. Okay, that part is important. So when Q is less than 1, that increases the driving force for that forward reaction. And then again, the cell potential is greater than, that's what we said right here, the non-standard cell potential is greater than the standard cell potential. Okay, when Q is greater than 1, that means you have more products than you do reactants. This decreases the driving force. I say that because that's how you would say it. When Q is greater than 1, that decreases the driving force, and the cell potential is less than the standard cell potential. Okay, so let's look at an example of this. So we've got that same reaction from above. We know that Q is going to equal the concentration of zinc 2 plus over the concentration of Cu2 plus. The concentration of zinc, they say, is 5 molar. The concentration of copper is 0.3 molar. I don't care what the answer is. All that I care about is I know just from looking at that Q is greater than 1. So if Q is greater than 1, and again, you can go back and look at this equation here on the equation sheet. If Q is greater than 1, then this whole thing here is a positive value, which means you're going to be subtracting a positive number, which makes your answer smaller, which means that the non-standard cell potential is going to be less than the standard cell potential. Okay? So predict the effect on the voltage of the cell. Well, whatever it was before, it's now going to be less than the standard cell potential is all you would have to say there. Okay? So when the non-standard cell potential is greater than the standard cell potential, that happens because Q is less than 1. And again, I don't ever use the term equilibrium with this. I just talk about it either is going to increase the driving force or decrease the driving force. Okay, when E is equal to the standard cell potential, then you know that Q is equal to 1. When Q is greater than 1, then the standard cell potential is greater than the non-standard cell potential. Okay, and then one more thing here. This comes up every now and then. Sometimes you might have a voltaic cell where it's the exact same thing on both sides, but one side has a higher concentration than the other. So this is called a concentration cell, and that's when each half cell has the same metal and the same solutions, but they're of differing concentrations. Okay, so that might be something like you might have, here's your voltaic cell where you've got, let's say, silver metal silver metal connected to a wire. You've got your salt bridge in here. Okay, and then this is 0.5 molar AgNO3, and this side is 2 molar AgNO3. Okay, when this happens, you basically are going to keep going until you get those concentrations with this to be the same. Now, when you have a concentration difference, electrons are going to flow from the half cell with the lower concentration to the side with the higher concentration. Now, why does that happen? Okay, let's look at our at what happens down here. So we need this number for those numbers to be the same. This side here needs to go down. This side needs to go up, which means we need to create more Ag plus on this side. So we need some of that Ag on this side, the solid Ag, to turn into Ag plus. That is an oxidation process. And so electrons are going to flow from here as that silver turns into silver ions, and thereby increasing the concentration on this side. Over on the right-hand side, this is going to be the cathode, okay, because the silver ions that are in here, the Ag pluses that are in here, are going to be plating onto the silver metal, decreasing this concentration. And that reaction will go until those two concentrations are equal to each other. Okay, so the key is to understand, first of all, remember that electrons aren't part of the concentrations or the masses. The electrons just flow from the anode to the cathode. Okay, so on this side, the anode side, we have to increase this concentration, and we do that by the silver metal being oxidized to silver ions that are now in the solution. On the right-hand side, on the cathode side, the silver ions that are in the solution must plate onto the silver metal in the reduction process where Ag plus is becoming Ag solid. And at that point, that concentration is going to start to go down. Okay? So in concentration cells, electrons always flow from the half cell of lower ion concentration to the half cell of higher ion concentrations. Okay? At that point, then you do actually, you can use that term equilibrium with that. An equilibrium has been set up where the electrons no longer will transfer. Okay? And then, yeah, since the lower concentration half cell is losing electrons, the metal electrode in that cell, we say dissolves so that it becomes Ag plus, producing more metal ions, and that ion, the ion concentration on that side is increased.